Hi, everybody. Welcome back to the Doctor is In podcast. I'm your host, Dr. Nadia Sabeh, president and founder of Dr. Greenhouse. Today, I am honored to have Dr. Bruce Bugbee on the show. Many of you listening have requested that I interview him or have asked why I haven't already. So this is your opportunity to listen in. Dr. Bugbee is a crop physiologist who has been studying plant nutrition, horticultural lighting, and environmental control of plants grown on Earth, as well as in space. Over his storied career, he's worked with NASA, invented an economical quantum light sensor, and been awarded the Utah Governor's Medal for Science and Technology. In the cannabis industry, which has historically been avoided by the academic community, Dr. Bugbee has become something of a superstar, or maybe a guiding star, for his willingness and ability to apply his expertise and know-how to cannabis science research, most notably around lighting. At a recent conference where we both presented, I learned that he has nearly 10,000 research article citations and almost 3 million views on his YouTube video, Myths of Cannabis Lighting, amongst many other YouTube videos that he's posted out there that I know are pretty popular in the industry. Bruce, it's so great to have you on the What Plants Crave podcast. I feel like there's a million topics we could discuss today: lighting, indoor versus greenhouse crop production, the reality of the movie The Martian. The list is endless, it seems like, but I know a lot of our listeners are coming from the cannabis industry and really want the opportunity to hear a deep dive into lighting, nutrition, and their impacts not only on the plant's growth rate and yield, but also how that environment affects product quality in the end. So, Bruce, thank you again so much for being on our show today.
Thanks for having me.
So let me just start with a little bit of your origin story. How did you get interested in horticulture and crop physiology in the first place?
I grew up in a rural area in Minnesota, and it was a farming area, but my family didn't farm. I worked on farms. But really, it was just when I was at the University of Minnesota at the time, but it was just I took a botany class, and it was just a fascination for growing plants. And that right away morphed into growing plants in protected environments. And I started working in the university greenhouse, and I was in engineering at the time. I started school in engineering, and then I gradually switched into plant biology. And I think that though interest and background in engineering has helped inform much of my plant biology research, because lots of what I study is really mass and energy transfer in plants. And those are engineering principles, as you know, but you apply them to movement of fluids in plants and conversions of energy, all those kinds of things. But to directly answer your question, my interest in plants didn't really start until I was around 20 years old and taking plant biology classes in college.
Yeah, I that makes a lot of sense to me, because as an engineer, the physiology part of the plant is definitely my favorite part, exactly for the reasons you mentioned, the mass and energy balance of the plant and even human physiology. I mean, it's just amazing how we are these thermodynamic beings that are interacting with our environment, and regulating our own internal environment based on the inputs and signals that we get from the outside. So because I want to try to focus on lighting, how did you get interested in horticultural lighting specifically when it comes to plant physiology?
I think a big turning point for me, I was in graduate school in California for a while, and then in Pennsylvania for a while. And then my first job after graduate school was at Utah State University. Turns out I'm still here. I mean, it was nonlinear. There were some other job opportunities along the way, but I'm still here. But early in my career, I got funding from NASA to at Plants in Space. And this merged the engineering part and the plant physiology parts. And NASA, right from the start, and this was way, way before LEDs, but NASA, right from the start, needs to grow plants under electric lights. You can't have a greenhouse on Mars or the moon, partly because there's no atmosphere and basketball-sized meteorites come hurling in and they break the greenhouse. And even if you made a balloon kind of greenhouse to bounce off those things, it has to filter cosmic radiation. And the sum of all those things means we basically put the greenhouse inside somewhere, and that means electric lights. And so that really jump-started my interest. And back then, it was fluorescent lights, and then we thought we died and went to heaven because we got high-pressure sodium lights. And then, of course, another big transformation to LEDs. But that was the initial interest. And really, if you're looking at a very protected environment, the ultimate is put it inside with just electric lights, no sun at all. And really, it wasn't for production. It was for research purposes only. We weren't thinking about, oh, this people will grow food this way. It's just understanding plant environment interactions in those early days.
So why was NASA interested in growing plants in space?
Feed the astronauts. If you're going to be on Mars, you're not going to ever have any fresh food unless you grow it. Now, you can grow wheat and rice on the Earth and ship them to Mars. That's real expensive, but you can do that because they keep. But anything fresh, tomatoes, lettuce, all the salad crops, you're either never going to have them or you're going to grow them. And in the case of growing them, of course, the plants recycle the water, they purify the water, they give us oxygen back. If you don't have photosynthesis, you got to have a way to get oxygen. So it not only do the plants provide food, but water and oxygen too.
Yeah, there's a real circular ecology that plants give us the opportunity in space. I have a question. You mentioned that going from fluorescent to high pressure sodium was like a godsend. So this evolution of lighting, fluorescent, high pressure sodium, and then LEDs also developed during, right? Was it developed for NASA or by NASA scientists, or did they just realize that there is a great application for LED lighting in space? But I'm kind of curious, like, what was the improvement from fluorescent to high pressure sodium, and then the next leap from high pressure sodium to LED? What made one technology better than the other?
Fluorescent is energy-wise, watts of energy out and watts of energy, and fluorescent is about 18-19% efficient. High pressure sodium jumps that up to about 35% efficient. So the efficiency doubled when we got high pressure sodium. But it wasn't so much that, it's that the energy was concentrated in a tiny little bulb. The bulb is 15 centimeters long and it's 1,000 watts. So we had a very concentrated source of energy, of conversion of electric energy to photons. And we suddenly could get up to full sunlight, really for the first time. You just can't get to full sunlight with fluorescent lights. So the growth chambers there was a lot more heat input. The compressors had to be bigger, even though it's more efficient. But we could do research under much higher light levels when high pressure sodium came along. And in parallel with that was metal halide. And the big concern then was, can you even grow plants under high pressure sodium? You know, the early ones were only 6% blue photons. And can you even grow plants? And it turns out they grew just fine, but we didn't know that in the beginning. And even then, it was common for people to mix high pressure sodium and metal halide in a 50-50 mix to get more blue photons. and really a better color rendering index for people too, because the orange tint of high pressure sodium is that doesn't have a very high color rendering index for people. So that was the big breakthrough, was to push plants harder, especially higher yielding crops that benefited from higher light. We could just do research at much higher light levels.
So you had higher light intensities with the higher pressure sodium lamps, but also you mentioned you weren't even sure if you could grow plants under low blue light levels. Was that sort of the impetus that started the understanding of red and blue wavelengths of light and how plants respond to specifically those two for photosynthetically active radiation, basically?
Yeah, to review the history of this, we were working closely with NASA all the time because they were funding us. And particularly NASA Kennedy, John Sager at NASA Kennedy had the vision that LEDs could become something significant. And back then, we were looking at sulfur lights and various types of technologies, many of which didn't turn out to work. Microwave sulfur, that's the lighting technology. Okay. And that has a really broad output. But this would have been in the 90s. I have to check the exact dates, but that's quite a long time before people thought about using LEDs commercially. But it didn't take long. And back then, the only one we had was red. There was no efficient blue LEDs. So it was like, okay, we'll use red LEDs and find some other way to get blue photons. And what's the minimum number of blue photons we can use? But we could see that LEDs had the potential to really be an efficient light source, even though they were really expensive and the early ones were not super efficient, but you could see where they could go. And now I should check the dates again, but maybe around 2000, Takahashi Nakamura got the Nobel Prize for a blue LED, and all of a sudden, the blue LED caught up and passed the red LED for energy efficiency, not photon efficiency, but energy. So suddenly, and then the blue LED meant that we could put phosphors on it and fluoresce and white and get white LEDs. So suddenly opened the door to all the colors. And this would have been 20 some years ago. And then they gradually kept getting better and cheaper. And that's when lots of commercial people started coming in. And I think not so much lighting companies just yet, but certainly researchers started looking at LEDs. And then 10 years ago, roughly, lots of commercial companies are making them, and it just exploded. And because we can get so many colors with LEDs, it really gave us more tools to do photobiology research. What do these ratios of colors really do? Before that, we always had to use filters. And one of my most highly cited papers is a paper with high pressure sodium and metal halide and filters. And it's about the amounts of blue light that different species need. But that work was done before LEDs were available. But it was also done because we knew LEDs were going to get there sometime in the future. So we wanted to do some studies on the fraction of blue photons.
So you said something that really interested me and kind of triggered some questions or other ideas about this blue LED, that once you had the blue LED, that you were then from there able to create more wavelengths of light, including the white LED, by adding a phosphorus coating or doing something else to that blue light. Because I'm guessing, like, just thinking about the the technology of that, or just sort of the science, the physics behind that blue light, is that it's a high frequency light, right? And so then you can sort of scatter the light in a way that distributes it into multiple different lower energy wavelengths, like yellow or red or beyond that even.
Yeah.
Yeah, that's really interesting.
That's the principle of fluorescence. And in fact, that's how fluorescent lights work.
Oh,
They have UV inside, and the UV fluoresces in all kinds of different colors, depending on the phosphor coating inside the fluorescent tube.
okay.
So that principle is well known, and you can always go from high energy photons downhill to lower energy. You can't go the other
You
way.
can't go the other way. Entropy rules in that
Yeah.
case. So, I mean, so how LEDs, the efficiency of producing LEDs and just the technology itself, is that what has really allowed plant scientists to isolate these wavelengths and really understand how plants are responding to very specific spectrums of light?
Yeah. Yes. The multiple colors of LEDs allow us to study things. Now, not every color is very efficient, so
Mm.
we still use phosphor-coated LEDs to create various ratios of colors. But oh yes, the LEDs have done an incredible tool for the fundamental study of plant photobiology. And in parallel with that, there's the recognition that there's commercial potential for doing this too. So in my case, commercial companies have funded our laboratory, not because they want to study basic research for NASA. They want to know how to make lights as optimal as possible for plant growth. So the commercial potential has resulted in more funding for the research too.
I see. I mean, have I have two questions associated with that. I want to try to stick with my initial question, which is, when using LEDs, or the research, the plant science research that's come out of using LEDs to study different spectrums of light, has anything come out that has been surprising about how plants are responding to these different spectrums of light? Or did we already basically know how plants were responding, but LEDs are just confirming what we had already figured out 30 or 40 or 50 years ago?
Yeah, that's a good question. If you really do the scholarship, and you're fundamentally aware of the literature back all the way to 1950, you can make the argument that very little of what we've done is fundamentally new. We already had a sense that the plants responded in this way. But I call that appropriate scientific modesty. As a young scientist, you think you've discovered something new, and then you go
Mm,
look at the literature and you go, oh, that people already really knew this.
okay.
And in the history of science, the people that get credit for many great discoveries were really people that explained the significance. They weren't necessarily the people that found it in the first place, but they recognized the significance and they could explain it in more clear terms.
What do you mean? Can you give an example?
Uh, I have to think. I have to go back to. I'm thinking of like Francis Bacon and scientists living hundreds of years ago. Now,
Okay.
not the last 50 years.
Okay.
And I have to think. It's a good question. If I make that statement, I should be able to back it up with very specific examples. And
We can give
I
you
have
a
to
chance.
think about it a
Yeah,
little.
yeah, we'll give you a
But
chance later as we're continue talking. You'll probably
yeah,
think of a couple good examples. Um, the other question that I wanted to ask you related to that is, you said that commercially you're getting funding to study these different wavelengths of lights for, I'm assuming, for different plants. A question that I always have when looking at the plant science or the scientific research around looking at 630 nanometers versus 650 nanometers versus tuning the spectrum for different stages of a lettuce crop or a cannabis crop, is it practical to apply these various spectrums in a commercial application? Or are growers just going to choose the most efficient or cost-effective broad spectrum white LED that kind of just covers it all?
Yeah, this is a good question. And the short answer is the importance of quantity of photons is always underappreciated. You've just got to have the photons drive photosynthesis. The effective quality of light, the ratios of colors, is overemphasized. Yes, we can manipulate plants with light color, but you've got to have the total quantity of light there. And even though I've spent lots of papers and a huge part of my career looking at ratios of colors, it's the quantity that is really critical. And a real specific example is because people don't always have access to high intensity LED fixtures, an enormous amount of the literature is done at low light levels, low photon fluxes, like 1 in 200 micromoles per meter squared per second. And I review papers constantly with these low light levels, and they show effects of ratios of colors. But I can tell you that if you get up to higher light levels, many of those effects disappear. If it's sort of like if you're starving, it matters what you eat. But if you have an adequate diet, you don't have to be so strict about what you eat. That's quality of food and quantity of food. So we have a lot of artifacts in the literature that a lot of studies in the literature that only apply to plants grown under very low light levels. And commercially, you just wouldn't use those low light levels. But that's taken us a while to discover that things don't, if things we learn at low light don't apply at higher light levels.
I am never going to listen to another lighting presentation the same again after you making that comment. So
and people that do that work often kind of don't even mention what their light levels were. I mean,
well, that's what I was wondering. I'm like thinking back even just to this summer and all the lighting presentations I've listened to is, when they're talking about lighting spectrum and red versus blue, and the different ratios of far red and red, et cetera, et cetera. Are they presenting the actual quantity of light, or are they right in those presentations? My mind is blown right now thinking about that. That the quality of light matters less the more light you have, and
yep.
the less light you have, the quality matters more. Now, when you make that comment, are you speaking specifically to yield and growth rate, or are you also speaking to maybe those, secondary metabolites, the color, the taste, the organic compounds, et cetera?
Yeah, all of those. We say plant growth and development. And what that means is plant growth means size, just fresh and dry weight of the plant. That's plant growth. Plant development means shape. Is it tall and thin? Is it short and fat? Those sorts of things. But both of those are affected. And mostly when we talk about the effective quality of light, we're talking about plant shape, because it's just flat out numbers of photons that drive photosynthesis. And yeah, we can tweak that a tiny bit with ratios of colors, but really not much. Photosynthesis is just fine under pure red light. there can be some synergisms with other wavelengths, but it's mostly plant development and plant shape that we're manipulating with light colors. And very specifically, it's photon capture. When we change colors, if we add far red, for example, the cells expand more and the leaves spread out and they capture more photons and they grow faster. But that's not a direct effect on photosynthesis. It's an effect on cell expansion and photon capture. Now, plants grow faster because they captured more light, and the photosynthetic rate was exactly the same. That's a real key distinction.
Interesting. Between
a direct effect of light quality on photosynthesis and an indirect effect on plant growth through photon capture. And that a huge amount of what we do with light quality is to get the plants to spread out more to capture the photons quickly, because if the photon falls in the ground, it's completely wasted. You want them to hit leaves as quickly as possible.
Okay, so let me see if I understood what you just explained. So under far red light, right, that's sort of the shaded canopy, right? That the plant, the leaves are reaching, they're trying to capture more photons, so they're spreading out more. It doesn't mean that they have more cells to do the photosynthesis. It's just that the cells are spread out more to do the same amount of photosynthesis as if they were a compact leaf under direct PAR radiation.
Mm-hmm. Yes.
Interesting.
Lettuce is a really good example of that too, widely studied. And far red is a good example of that. You can make the leaves broader with far red, and the plant ends up growing faster because it got more light.
Mm-hmm.
Blue, of course, is the opposite. Blue shrinks the cells and makes the plant more compact. So we play with ratios to make the plant think that it's in the shade when it's really not in the shade.
Oh, interesting. All plants? Like I'm thinking about, so if I thought about a tall crop like cannabis that has multiple levels, I guess you could say, right, layers of leaves, versus a compact plant like, say, a lettuce plant where it's kind of shading itself in a different way, does one of those crops benefit more from a higher far red ratio than the other one?
We call plants shade tolerant and shade avoidant, or shade avoiders. And a classic plant that's a shade avoider is like bindweed. That gets real tall under far red light and its heads up. The stem extension is enormous and it gets tall fast because it perceives it's in competition for light. And if it can get taller, it can get to the top of the canopy. Well, that's universally bad for controlled environments. We don't want tall, skinny plants. Lettuce is the opposite. That stays short and spreads out horizontally. So we can use things like far red light to improve lettuce growth. And in the case of cannabis, very tricky because the plant tends to get taller faster than it gets wider. If we could use far red and make the cannabis plant get wider, that'd be terrific, but we can't. It makes them tall fast. So we have to be very careful about the application of far red photons with a crop like cannabis.
Interesting. It wants to stretch above its competitors, basically.
Above its neighbors, yeah.
Interesting. So I want to step back for just 1 minute because we're talking about quantity versus quality. Can you talk a little bit about the different metrics that are used to quantify quantity and quality of light? I know that, I've seen you give presentations about DLI with cannabis and how it's, very hungry, light crop, very light hungry crop. But can you, just for our listeners, kind of bring us back to earth for a second and just talk about 2 or 3 of the most important metrics that growers and even scientists are using to monitor light utilization or delivery to a plant?
Yeah, I would think most growers know about PAR, photosynthetically active radiation. and then more technically, more specifically, photosynthetic photon flux density. Those really refer to the same thing. One's is just a more precise technical term. But we have lots of excellent, relatively low-cost sensors now to measure the flux of photons coming in. And there's a bunch of hobby grade sensors that are good, but they can drift over time, and research grade sensors stay stable for longer. So those are pretty critical sensors for people. And even to this day, it's surprising that people have big operations and they don't own a quantum meter or a light meter. Gosh, how do you know? Do you have a pH meter? Well, of course. And I said, well, a light meter is probably more important than a pH meter. But so that's a fundamental measurement. And then in recent years, as we have discovered that far red photons, which are deep, deep red at the edge of our vision, those are photosynthetically active. So now we have a new definition of photosynthetic radiation called EPAR, lowercase e, and that stands for extended range photosynthetically active radiation. And of course, you can get sensors for EPAR now too. And if you have far red, like a greenhouse, EPAR is the preferred measurement. And even under electric lights, EPAR is a better representation of the total photosynthetic radiation. Now, when we get into quality of light, that's a lot harder. Now you need to separate the bands of colors, and that typically requires a spectroradiometer. And those have continued to get better and cheaper. There's handheld models. My company, Apogee Instruments, just came out with a new one that has a screen right in the meter. You can make it, and it fits, you can hold it in the palm of your hand. So it's better and cheaper. But those really are important in research to understand what colors of light you have. In a greenhouse, the sun's moving. We know the sun spectrum. It's the same from day to day. It's less critical to have a spectroradiometer than it is in electric light agriculture. But those are 3 times as expensive as quantum sensors. So, and really a good lab ought to have one of each, a quantum sensor and a spectroradiometer. But those are the primary tools to measure light quantity and light quality.
Now, based on our earlier part of our discussion, when you said that if you have enough light, quality doesn't matter as much, does that mean that a spectral radiometer, if you have enough light in your commercial operation, maybe is a nice to have and not a need to have?
That I would say that's right. Yeah.
Okay. What is enough light? Like what is the quantity of light? I feel like I should have asked that question earlier, and I'm sure it's different for different plants. But what is that? Is there a threshold of the quantity of light at which the quality matters less?
It's not a sharp cutoff.
Okay.
It's a gradual thing. But in terms of metrics for quantity of light, and as you know, and it's worth saying this again, what the plants really respond to is not how much light they're getting per second, but how much light they're getting per day. And so we call that the daily light integral. And now there's meters that measure this every second and automatically add it up, and with a digital display of the daily light integral. That my company, Apogee Instruments, sells one like that, and it gives you the daily light integral. So let's take lettuce and cannabis, because those are 2 real common crops, and they're very different for quantity of light. We would like to get lettuce up to a daily light integral of about 20 moles of photons per meter squared per day. Now that's in the summer, that's only 1/3 of summer sunlight. But in the winter, it's like triple or quadruple the natural sunlight. So you got to supplement in the summer. But around that range is an economic optimum for lettuce. It'll grow faster if you give it more light, but it starts to get tip burn depending on the cultivar, and then can become unsaleable. So it gets hard to push lettuce with light levels higher than 20 moles per meter squared per day. In the case of cannabis, that crop, I don't ever say it's light hungry, it just benefits from higher light. That crop is just getting started at 20 moles a day. And we have a study going on right now with cannabis. We're giving it 100 moles per meter squared per day. That's almost twice full sunlight in the summer in the field.
Wow.
Now, that's not an economic optimum, but we're testing physiological optimums.
If it has a limit, it has to have a limit.
Well, it does have a limit. And for sure, it's going to be up around 100, it might be 80, but I mean, this is super high light and super fast growth rates. Everything has to be optimized all the time to grow the plant that fast. Like taking a car to the Bonneville Salt Flats and driving at 800 miles an hour. And you better have good tires and good suspension. And that's a unique car. It's not just a big engine. Everything else has to be just right to go that fast.
Yeah.
And that's the case with cannabis. But cannabis easily in all of our studies benefits from like 60 moles per meter squared per day. Now think of the stress that puts on the HVAC system. That's just a huge flux of water, latent heat.
Yeah.
Oh my God, this is life in the fast lane. You can't just put cannabis in a regular greenhouse and turn the lights up. Everything else has to be, nutrition has to be optimized, watering has to be optimized, CO2 has to be elevated. But when you do that with cannabis, that's one of the things that makes it such an exciting crop. Man, it can grow and yield at very high levels in very high light.
I mean, why do you think that is? Why is cannabis so unique in this way?
It's not totally unique. Corn is like this too.
And you can hear corn grow, right? Yeah. It grows so fast. So can you hear the cannabis plant grow? Have you tried?
No, and it's even, you got to be listening pretty close to hear corn grow too. But you can hear leaves expanding. Part of it, we're studying this now, but part of it is much of the photosynthetic capacity goes to the emission of volatile compounds. And in the case of cannabis, that's terpenes.
Interesting.
If you walk in a field, you can smell the terpenes from the cannabis. Well, those came from photosynthesis. So the photosynthesis is high, then it off gases all these terpenes. They don't become part of the dry weight of the crop. They just make gases that are emitted. So that part of what helps it to have such a high photosynthetic rate. But it also it just processes photons really fast. Now, when we get into it, there's other crops that are pretty fast too. Corn is a good example. So it's not in this unusual class all by itself, but it's sure in a rarefied company where not many other crops benefit from those super high light levels.
So if those photosynthates are terpenes or these volatile organic compounds, that immediately triggers for me potential issues for cannabis growers who are trying to reduce the emission of odors from their facilities. So are we sort of indirectly implying that increasing the rate of photosynthesis of cannabis by higher light levels, more CO2, higher temperatures, all of those inputs that need to happen together that we are inadvertently then increasing the odor emissions from these crops, that it might actually be more challenging under this higher light environment to control or mitigate odors? Or there's just more of them?
There's just more of them. If you double photosynthesis, you double the emissions. And
It's linear
not,
like that?
not just, well, that's a rule of thumb, right?
Okay. Okay.
And I don't know if it keeps doubling and doubling on all that stuff. I don't know if it's a linear effect exactly, but it's a good rule of thumb. But so what? I mean, what if the emissions are, in most crops, the emissions might be as high as 5% of the total photosynthesis. We're working on this now, but cannabis might be 20%. Well, that still means there's 80% for something else. So it's not a no-win game. But if the plant grows bigger and faster, it stands to reason it's going to have more emissions. And if those are unpleasant and you got to filter them out, yeah, well, you have more to filter out. That's a good example, though, of design of a facility. If you design it to have really high light levels, you might also have to increase the amount of carbon filtration to reduce the volatile emissions to the neighborhood.
Interesting. A
So
new question for us to think about.
Yeah, lots of things scale up.
Yeah.
All of them with quantity of light.
Interesting. So at 100 moles per day of DLI, can those cannabis plants just grow under any light spectrum and they'll be happy?
Yeah, pretty much. I mean, you want to have very efficient LEDs to get that high, but it's not quite black and white. It's not like the quality doesn't matter at all. It just matters less.
Right.
We give the plants a very low fraction of blue photons, and has not to do with their growth. It's because red LEDs and red photons are just energetically more efficient.
Yeah.
So it's an electrical efficiency issue much more than it is a photobiology issue.
I've been thinking about that. We've been, working with California on the energy code regulations that they've been developing, and, this push for higher light efficiency, right? Photosynthetically photon efficacy. I can never get that acronym right. PPE. The number of watts and the number of joules you put in, and the number of moles you get out. But I think a lot of the regulators don't understand that by pushing this PPE number higher, this threshold higher, that we're really just pushing the LEDs to more and more red diodes.
That's right.
So at what point do we reach a PPE at which it's just all red light, right? Is somebody pushing back and saying, well, hey, we still need this small fraction of blue light or other wavelengths, so there is going to be a limit for what the PPE can be, because otherwise it's just going to be a red diode?
Yep. The reason we put the typical fixtures now are, maybe 5 or 10%, 5, 10, 15% white LEDs, and the rest reds. That's commercial fixtures have all coalesced on that. And the reason we put whites in there is so we can see the plants. That is for the people. If you have pure red LEDs, you can't tell if there's insects on the plants. You can't tell if there's diseases. You can't tell if there's nutritional disorders. You got to have white LEDs to see the plants. Now, in addition to that, those white LEDs add some blue and green, which are very useful supplemental wavelengths. But because the LEDs are less efficient, we just try to minimize the white LEDs. In our case, in our fixtures, we've got 80% red, 20% white. And that's not as efficient as it could be because of 20% white, but it's research and we can really see the plants. The color fidelity index of that is much, much better. and we can examine the plants for subtle nutrient disorders, microscopic insects. Those are the reasons the whites are in there, to help the people study
Yeah.
the plants.
Yeah. Anyone who's been in a vertical farm with just red and blue, basically pink light, knows
It's pretty bad.
it's hard to get used to. That's
Yeah.
for sure. um uh what was the next question?
Nadia, on that
Yeah.
note,
Yeah, please.
some people have said, just give them all red and wear a headlamp, and
Oh,
with a
sure.
white headlamp.
Sure.
Yeah, and we tried that, but it's nothing like looking out across the entire crop to be able to see how it's doing. Uh,
Right.
so
Right. And it's
we,
easy to miss certain things with the plant, right? If you're scouting for
yeah,
insects, or you're scouting for tip burn, or you're scouting for different diseases, it's harder to observe under this pretty unnatural
yeah,
combination of light spectrums.
yeah,
Yeah. So, Bruce, I mean, one of the questions I want to ask, since I mean, you're doing this research to push the limits of the cannabis plant, but what I feel like I would be doing a disservice to the industry if we walked away from this conversation and growers went out there and they're like 100 moles, right?
mhm,
Like, it's just blast these plants with the brightest, sunlight possible, and blind all of our people, and probably the plants too at some point. For practical purposes, what DLI and or light intensity, right? Because if we're looking at a flowering crop and it's, let's just say, 12 hours of lights on, then we are limited to the photo period in which we can achieve our target DLI. But what would you recommend growers target for their DLI for a cannabis crop for, say, the veg and the flower stages? They're different, right?
yeah. I wouldn't say veg and flowering are different. I always just say they're the same.
Really?
Yeah.
Interesting.
I mean, veg, it's easy to get higher light because you have 18 hours of photo
Oh,
period,
that's true.
but you might as well take advantage of that and give them high light in
Yeah, and the
veg.
faster they grow, the quicker they're going to go into flower and the more cycles you're going to turn
Yeah,
over.
yeah. Um, but gets into the issue of a physiological optimum and an economic optimum.
Mm-hmm.
And we often don't have a good appreciation of the difference. Just because I can show you can grow cannabis at 100 doesn't mean that's the economic optimum. And the economic optimum is, of course, depends on more types of inputs, and it's harder to study. But right out of the gate, the economic optimum for cannabis depends on the cost of electricity, the cents per kilowatt hour, and the value of the crop. And if the electricity cost is low and the value of the crop is high, I'd give them 80 moles a day. But if the electricity cost is higher and the value of the crop is less, that optimum is going to drop down to 30 or 40 moles a day. So there's a range from maybe a low of 30 to maybe a high of, I don't know if I'd go to 80, but 70 anyway. A big, big range for an economic optimum.
Mm-hmm.
And boy, that depends on a lot of things. What's the cost of the lights to put in? Some growers can't even get the power to give them
Yeah, that's
60
true.
moles a day, even though it'd be great, but they can't even get the power. So
The
it's
HVAC equipment that's going to have to then pull out all that energy, both the sensible and the latent energy, is almost equal to the energy we input with the light. So you also have to think about
yes,
that.
yes.
Yeah.
So when you say an economic optimum, it depends, but I would put it at 30 to 60
Okay.
moles a day. That's a twofold range, but in that ballpark.
And I feel like most of the growers that we work with and that I talk to, that is what they're targeting, is somewhere between 30 and 60. I'm hearing more growers pushing it towards 50. Very rarely am I hearing them say 60. Maybe they're trying that in their R&D, right? They're playing,
Yeah.
they have the light fixtures where they could hit 60, but they're really dimming it, right? I almost feel like they like knowing that they could achieve that, even if that's not what they're going to produce at. But yeah, I would say 40 and 50 are the two that we hear the most frequently with cannabis. And even with lettuce, I mean, it's very rare to hear 20, I would say, right? I mean, especially for the winter production cycle, if growers can get something 12 or better DLI, then they're pretty happy about that.
That's because lettuce is not as valuable as cannabis.
Sure.
Per gram of weight. If lettuce was more valuable, we'd be putting 20 on lettuce.
Sorry.
It definitely grows faster. If you increase DLI from 10 to 20 in lettuce, you don't double the yield, but you might increase it by 1.8.
Mm-hmm.
And so your efficient use of electricity is a bit less.
Oh.
So that's where there's like a number of 12 moles a day for lettuce. That's more of an economic optimum. And that's way below the physiological optimum for lettuce.
Right. And, for a greenhouse lettuce grower, they're thinking about supplemental lighting in the winter, not necessarily in the summer. And so anything they can do to boost that yield and that growth rate in the winter to maybe not be the same as the summer, but as, better than they would without it. Then yeah, greenhouses tend to be a more economical equation.
Yes.
Right. Yeah. Pinching the pennies and much thinner margins. So having just a little bit of supplemental light goes a long way than having none with a greenhouse lettuce crop. And they're less photo period sensitive, right? The lettuce crop.
Yes.
I mean, if we're just looking at these two crops specifically, I mean, like you said, we have 12 hours. That's all we have for cannabis. But for lettuce, I mean, some growers are trying 24 hours, right? Trying to figure out if lettuce plants even need a resting period. I feel like every living thing should have a resting period. Give it a break. Give it a nap, at least a power nap. But yeah, we can at least push it to 18 or 20 hours to squeeze out a few more photons for the day. Going back real quickly to the spectrum, a few of the questions that I had to do with the secondary metabolites and the quality, the end product quality of the crop, especially with cannabis. As markets are declining, as they're getting squeezed, as prices are falling, and at least here in California, I know in Massachusetts and a few other states, there's more emphasis on the quality of the end product than necessarily more. And so I wanted to ask you, with those other wavelengths of light, we've been talking a lot about PAR and DLI and, the quantity versus the quality, and maybe the quality doesn't matter as much if you have more quantity for yield and production purposes. But are there, you also mentioned, having more photosynthesis, we get more VOCs, which I would consider those compounds being also secondary metabolites. But is there something else in the middle? If we just concentrated red and blue light on a plant, are we missing opportunities for flavor, color, the sort of aesthetic, even the nutrient content of a plant that's maybe not cannabis? Maybe cannabis is very nutritious. We just don't eat it very much. I'm just curious if you could talk about quality a little bit.
Well, we use blue light a lot to turn lettuce red. And many red lettuces stay green if they don't have blue light. So there's an example, and that red is anthocyanin pigments. And so in the case of lettuce, yes, there are secondary metabolites that can result in flavor and nutritional quality. So that argues for more blue light in the spectrum. Now, how much? 5%, 10%? In the case of lettuce, people don't realize the two most powerful, we always talk about using blue light to turn red lettuce red, but the two powerful things that turn lettuce red are high light, it turns red, and lower temperature turns red. Those are real powerful techniques for making lettuce red. blue light's way down on the list of
Really?
things that make lettuce red. So we don't talk about the primary things that do it, or at least they're not appreciated by many growers, and even not appreciated by many research scientists. But there's plenty of literature on that.
Because I've heard anthocyanin be sort of compared to the plant's natural sunscreen, that under UV and blue light, that the plant is producing anthocyanin to protect itself. I could see the same argument being made for that high light intensity, that yes, oh my God, it's so much light, I need to protect myself.
Yeah.
But the low temperature is interesting. Is it a freeze protection then?
No, it's just cooler temperatures.
That's it?
Anthocyanin just degrades faster at higher temperatures.
Okay.
So
Interesting.
yeah. In the case of cannabis quality, that's all over the map. That's just like wine, which type of wine is, and we like to have high terpenes. A lot of cannabis quality is determined by how we cure the plant, how dry we get it.
Right.
Terpenes they're tricky because the low molecular weight disappear anyway, no matter what we do. And the high molecular weight sesquiterpenes stay in the plant no matter what we do. And there's just a few right in the middle that we're trying to preserve, that we have the potential to preserve. But terpenes are, consumers want to see high terpenes. They want to see just the right color. I mean, purple, for example, in cannabis is a prized color. Well, turn down the temperature the last couple of days to get purple. That's a really powerful technique for...
Make my job even harder by turning the lights up to 100 moles per day and asking for a 60-degree temperature.
Yeah, that's right. And we often don't do it because it's... engineering wise, it's hard to do.
It is. And going back to the economics of the amount of power you would need to run lights really high and the air conditioning really low. Oh my God. Yeah. You better be selling that purple weed at a really premium price to make that pencil out.
Yeah.
Yeah.
But you could turn the lights down at the end too.
Okay.
For example. But quality in cannabis, it's very, very hard to get 10 consumers to agree on exactly. And so mainly they look for high THC, just getting that high. And that's mostly genetics that get THC high. High light helps, but it's mostly genetics that result in real high THC.
Okay. So as we're wrapping up our discussion today on lighting, I just wanted to give our listeners the opportunity to learn about how you came to invent Apogee Instruments. I learned about this when we were in Toledo together, and I thought it was so interesting that as a research scientist looking for this practical way to measure light, you basically stumbled upon inventing this instrument that's now commercially available to everyone. So can you just tell us a quick story on how that came about?
Well, because of my early background in engineering, and especially electrical engineering, I knew how to modify voltmeters to take them apart and modify them. And I also knew that there was a photodiode that had the approximate characteristics of PAR, of photosynthetic radiation, 400 to 700 nanometers. So I started modifying voltmeters and gluing this photodiode on the top of the meter. It was a real simple thing. And then we would calibrate them in our growth chambers and they'd be fine. And at the time, the commercially available meters were more than $1,000. And so I could make this thing for $50, and I started building them. And then colleagues would come to visit and they go, "Oh my God, could you make me one?" So I'd make them one. And then I started to get requests from people I didn't know. I'll buy one. I'd like one of these. I saw it. Ted Tippett's laboratory. And I went to the university and said, I'd like to start a company, or I'd like to have a separate account to keep track of this. And the university said, sure, we'll help you start a company and we'll take half the money. And I said, well, that's okay. I'll just do it, keep doing it at home. And that's how the company got started, real low tech like that. And at one point, that about the NCERA committee, in the early days, that committee voted to pay me to build a light meter for everyone on the committee. That was, at the time, it was an order for like 50 or 60 of these.
Wow.
And I was building them at my kitchen table. And so I hired some students and we scaled up and moved into my garage. And those are the early days. And then the meter just kept modifying it, getting it better and better. But it was in my garage for 8 years, the company.
Wow.
Until it just got too big. We had to move out to a commercial facility.
Do you know how many meters you've sold to date?
Oh, God. many tens of thousands.
Wow.
They're sequentially serialized,
okay.
But yeah, maybe it's 100,000. I don't know, but
that's amazing.
It's almost 25 years later, and it's in the beginning. I thought, oh, we will build a few hundred, and that'll saturate the market, but the market's just flat out expanded.
Yeah.
Electric lights, you got to measure those. So
I mean,
it was a very modest beginning.
I mean, but what I love about this story is that you invented something out of need and out of personal need, right, for your research, that sort of organically expanded because it was something that everybody needed and created a standard within the industry that people could rely on. I find that to me, those are the best inventions or creations, are the ones that come from the personal need to improve the technology or the methodology that you yourself are using.
Yeah. No, in the very beginning, I didn't intend to start a company.
Right. Exactly. Yeah. Yeah. It wasn't just technology for the sake of technology. It was technology for the application of science. It was perfect.
Yeah.
So just to wrap up the last couple of questions here. So how have you seen the industry in general? And you could focus on cannabis or horticulture or lighting, but how has it evolved in the last 40 years or since you first, started doing research or working with NASA or taking that first plant biology class? Yeah. How has it changed?
The biggest single thing is the commercial application of this, using electric lights to grow food. Just flat out that. We were already using greenhouses to grow food in a limited way, but now that electric lighting technologies become so efficient, it's being applied all over the place commercially, and that drives a huge demand for more research. Before that, it was doing research to predict what plants would do in sunlight in the field.
Right.
And that was going on for decades. Controlled environments were a really powerful research tool to understand plant responses to the environment. But then that morphed into a commercial thing and morphed and exploded. And now, oh my God, the horticulture meetings, we had one little group in the early days, 40 years ago, with maybe 10 people that met as part of the Horticulture Society. And now the last horticulture meeting, there were 8 major sessions on controlled environment agriculture. And that's what's by far the most. I mean, other groups might have had 1, maybe 2 sessions. And those rooms were packed, standing room only in the back.
Wow.
We went from a couple people in a closet to the dominant part of the whole horticulture society right now, because there's so much commercial interest in this.
Yeah. Yeah, I mean, I've seen something similar, I mean, through my career in general, but even just in the mechanical engineering, the HVAC engineering industry and societies and circles. I went to my first ASHRAE meeting actually in Utah, in Salt Lake City,
Hmm.
in 2008. And I, attended the technical committee on plant animal environments, and there were like 5 or 6 of us in the room. And fast forward to 2019, and it was standing room only also. They did not give us a big enough room because historically, right, it was 5 or 6 people, 10 people, say. And all of a sudden we had 40 people, engineers, mechanical engineers in the room trying to, right, just get a better bearing on what this industry is about and how they can help it, right? How they can service this industry through their design and manufacturing and research, et cetera. And yeah, still to this day, I mean, the last meeting I went to this summer in Florida, there were 20 people in the room, and that was the summer meeting. Like, that was the small meeting. So
Mhm.
and now there's multiple committee meetings focused, or committees focused, or talking about indoor agriculture, and how to look at energy, how to create design standards, how to support the industry in general. But yeah, again, going back just 15 years, there are, half a dozen people in the room, and now the whole society is paying attention.
Yeah,
It's
yeah,
exciting times for sure.
yeah.
So I'm going to ask you another question and kind of turn that on its head. What do you think is not going to change in this industry in the next 5 to 10 years?
The fundamental interest in plant environment interactions and
Mm,
optimizing plant growth from a science perspective. That's going on a long time, and that's not going away. I also don't think another thing that's not going away is what I call high input agriculture. The
okay.
extent to which we use electric lights, well, we're always going to be using them because they're not going to get worse. But high input agriculture means more inputs so we can get higher yields per unit area. Then there's always less land, so we're pushing to get higher yields,
Yeah.
and that's pretty permanent. Now,
That's
high
been
input,
fundamental of agriculture for the last 10,000 years, right?
yeah, exactly. That's why it's pretty safe to make the prediction that's going to continue.
That's not going to change. Fair enough. Fair enough.
But it's higher and higher inputs to agriculture, and it's tricky because those inputs are often more energy. And
Right.
so, how
More
are we going to say
resources in
that?
general.
Uh, when I say indoor agriculture, I always include greenhouses. They are indoors. That is indoor agriculture. If you don't use the sun, then I call that electric light agriculture.
Mm,
As a distinct caste,
yeah.
it should be called electric light agriculture. If you say indoor agriculture, well, that uses sunlight, and that's a huge difference. So the extent to which we keep doing electric light agriculture, it depends on cost of energy, the economic of energy, but it's really difficult to say that's more sustainable when it requires much, much more energy input. Sunlight's free, and now we're going to burn fossil fuels to make electricity and use the electricity to make photons again. We ought to be doing everything we can to make direct use of free sunlight.
Yeah.
And that means high-tech greenhouses. So I see that the future of high input agriculture is high-tech greenhouses with unique glazings reflecting the thermal infrared radiation. Um, they're still going to use LEDs to supplement light in the winter, but
Hmm.
when you reflect thermal radiation, now you can air condition the greenhouse.
Yeah.
In fact, I'm sitting next to my home conservatory where I have that glazing on it, and I hardly need cooling
Wow.
because it's so efficient. Um, I see that happening, and I didn't, but I could have air conditioned the greenhouse. And then when you do that, you can do two things. One, you can elevate CO2, so
Mm-hmm.
plants grow a lot faster. And then two, you can recycle the water
Right.
because you're condensing the humidity and just run it back for irrigation. So water use efficiency goes way up. Now, people talk about that, but as you well know, the claim of much better water use efficiency, let me put it this way, it is not yet being achieved.
Right.
Even though it can be, and typically it's just not. We use evaporative cooling for cooling that uses massive amounts of water. There's a lot of misperceptions
Right.
about things.
There is. And even a lot of greenhouses, even taking the evaporative cooling piece out of the water balance equation, which most people do anyway, they're not paying attention to that, right? Even on the irrigation side, how many greenhouse growers or even indoor growers are recycling and reusing the leachate, the drain water, right? The water that's not being used by plants. It's kind of shocking that even in a hydroponic system, how many growers are not reusing that water.
Yeah.
And I get it's complicated, right? Like the equations, the chemistry is complicated because then you have to measure what's coming back and you have to supplement, right, the water, and there's math involved in that. That's hard. Also the filtering that's required, right? And the sterilization that's required because you don't want, to bring something back and then send it back to your plant. So there is more design, there's more math, there's more infrastructure that's required to do that. But if we're making claims broadly, the industry making claims about we are using less water or can use less water, I just want to see more people doing that, applying it even at one system level, let alone all of them.
Well, we're working hard on that.
Yeah.
And actually, we're working hard on that with NASA funding.
Oh, good.
NASA doesn't even have an option.
Oh, that's true. Yeah. What are they going
to
to do? Dump it out into space?
Yeah. So in fact, last year we published a paper. That's my students and I. The title is Principles of Nutrient Management.
Okay.
And I think it's in regenerative agriculture, but principles of nutrient management. And if the listeners type in my name and principles of nutrient management, that'll be the top hit.
Okay.
And that's a long, comprehensive paper on how to manage nutrients so you don't have any leaching.
Well, thank you for publishing that because it's a resource that I think we all can benefit from to understand what that nutrient balance is. It's a mass balance. And, certainly even just thinking about, we're talking about the inputs and having highlighting levels, the right temperature, the right CO2, but the nutrients are a major consumable. And it's also a cost, a resource. And where are we getting those nutrients from? That's a whole other conversation we could have. But if we can reuse those nutrients and manage them and not overuse them. I know you've talked before about, high phosphorus levels and other nutrients that we're not, that plants don't necessarily need, but we just have this mentality as humans that more is better. But that's not necessarily true. So, I'm very interested in reading this article, and I hope our listeners are too, to understand exactly, what that nutrient balance needs to be. Is it specific for a crop, or is it different crops, or is it sort of crop agnostic?
No, crop agnostic. It's all crops.
Nice.
The examples many of the examples are with lettuce and tomatoes, but it's for all crops.
Yeah, it applies across the board. So, Bruce, last official question for you. What do plants crave?
Light.
I would have been disappointed if it was any other answer.
People talk about that for nutrients all the time. They must be craving some nutrient. But light's the biggest factor that drives everything.
Yeah.
And
We wouldn't be around without light.
yeah,
Light
yeah.
is life. Yeah. Okay, so I'm going to end with my rapid fire questions, Bruce. So I do this with all of my my guests, and they're just meant to be one word, one sentence answers, real quick. If you want to expand on anything, of course you can. But keeping it short and sweet is great. So, are you ready?
Okay.
All right.
It sounds like some kind of test.
But a fun one. All right, first question. Are plants introverts or extroverts?
No, we don't apply anthropomorphic principles to plants. That's a recipe for coming to bad conclusions.
So you're not going to answer the question?
It's not a question that applies to plants. Yeah.
What would be an
You
equivalent question?
you could anthropomorphize and say Little Shop of Horrors, that was a extroverted plant.
Yes, it was.
That was a science fiction story too. So, but you could play around with that. So I'll say,
All right.
in a
Plants
science fiction
aren't
way,
people.
it depends just with plants, just the way it does with people. How about
Okay.
that?
They all have their own personalities. How about that?
Yeah.
What have plants taught you?
Caring for biology, caring for another living organism,
Okay. I like that.
and helping it thrive same way you do with the pets.
Sure.
Um,
What about cannabis specifically? What has it taught you?
mm, the highlight thing is pretty fundamental. That's pretty interesting.
Okay.
Um, it of course right off the bat you see just a boatload of myths from people's observations that these cannabis heritage growers are really keen observers of cannabis, but they don't have a background in mechanisms.
Mm.
And in an engineering sense, if you know how to do calculations on latent and sensible heat, but if you didn't have that background, you would just say, well, that size of a dehumidifier looks about like it would work. And then you would write a story about how this is the key dehumidifier you should buy because I bought it and it worked for me. But the moral of this story is the science background helps you associate observations with mechanisms, and that helps you filter out, that helps you gain knowledge. When observations and mechanisms agree, then you probably understand the system. But if observations and mechanisms don't agree, you got to admit you don't understand what's going on. You make new calculations and you more careful observations. That science spirit is not well developed among heritage cannabis growers because they don't have the background to think about what would be the mechanism to cause this to happen.
Yeah. They just know it does happen. And I think that's also, I agree with that. I think that's something that's really impressed me about this industry and about legacy growers is that they had an intuition or long-term experience with certain plant responses that they didn't necessarily understand the why behind it, that mechanism, but they understood that it did happen. And what I'm loving is how now that we are applying the scientific method and doing research on this plant, that we are coming to really similar or the same conclusions that these legacy growers for the last 40 or 50 years have been telling us or have already observed. And now we're just validating those observations in a lot of cases.
Yep.
Yeah, it's pretty cool. Can controlled environment agriculture be a sustainable farming practice?
Oh, you can argue that none of agriculture is sustainable. To the extent we use fossil fuels to drive tractors, what we have done for the last 100 years is use fossil fuels to substitute for human labor. And human labor is really efficient. But that's not how we practice agriculture in
Yeah.
developed countries. We use fossil fuels to make it labor efficient
Right.
and often economically efficient too. The cost of the fossil fuels is way cheaper than the value of the product. But this doesn't apply just to high input agriculture, it's all agriculture. But really, the higher the input agriculture, generally the less energy efficient it is. But the more labor efficient it is too. So we can automate and look at in electric light agriculture that can work economically because we can automate it.
Right.
We don't have to have people doing the harvesting. And so sustainability for human labor is really good, but energy sustainability is not. So to say something that uses energy to make it go better, I mean, how about driving to work versus riding a bicycle to work?
Mm.
Yeah, well, the bike is more efficient. Well, how about just walk to work? That's more efficient than
That's
riding
even
the
more
bike
efficient.
too.
Yeah.
Yeah, but with that analogy, you think walk to work. That's ridiculous. That takes me an hour. No way I'm doing that. Yeah, well, it
Right.
didn't take much energy to get you to work either.
That's true. That's true. Um, that makes me think then even more efficient would be to walk to work naked, because then you don't have, right, the clothes that took energy to make that
Yeah,
and to ship it to you as well. Like just
yeah.
strip it all down.
There you go. If you live in a place where the climate's right, yep.
Yeah, there you go. Otherwise, it wouldn't be very efficient because
Yeah,
our bodies would be working so hard to keep us cool or warm.
yeah.
All right, last question. If you could take only one plant with you to space, what would it be?
Mhm. To survive, I would probably take wheat because you can make that into so many different things. It's just such a fundamental
Mm,
staple. And that's obviously not an emotional answer. That's just how
yeah,
long am I going to survive?
a practical answer. But I thought
Yeah.
everyone says that wheat you can't grow efficiently or effectively or economically indoors. So why would we take that plant with us to space?
It's Wheat's a good example of it's cheap in the
Mm,
field, but in space, you asked me in space,
I
not
did.
on the ground.
I did.
And if I only had one food product to eat, what I eat? Well, you think, oh, I love tomatoes. I'd bring tomatoes. Oh, really? That's going to be your diet? It's only tomatoes? Or if you make wheat, you can do bread, you can do cookies, pasta. You can make it into a whole bunch of food products.
Right.
And it has the right ratios of protein and carbohydrates. And so,
It reproduces seed, so you can keep
and it's
replanting.
you easily can harvest seed and
Yeah.
replant it. Yeah. Um,
So the Martian, he would have been better off, do you think, with wheat as opposed to potatoes?
Potatoes are pretty good, um, but they're low protein. And so in
Okay.
the long term, if he was there long enough, he definitely would have run out of protein.
Mm.
But potatoes are high yielding and lots of starch. But yes, he would have been better off from a diet standpoint with wheat.
Yeah. And he wouldn't have needed so much ketchup.
Yeah,
Which comes back to tomatoes.
yeah,
Well, Bruce, thank you so much for this interview and for being a guest on this podcast on What Plants Crave. I really appreciate talking to you, having the time to talk to you one-on-one. We see each other a lot at conferences, but we rarely get the opportunity to just
yeah.
have a conversation. So this was really nice.
Good. Well,
Yeah.
good luck with your podcast and everything else.
Thank you so much, and enjoy the rest of your summer and have a great new school year.
Yeah, thank you, Nadia.
All right. Bye,
Yep.
Bruce.
Bye now.